Okay. Hi, everybody. Sorry for...
Ma no, non serve.
Can you hear me, right?
Yes.
Okay, very good. And I can hear you. And I'm very sorry for this problem, but I have COVID, as you know, so we cannot meet in person. Okay, so I just updated the outline document in the share folder, and this is the lecture for today. So I would like to start with a recap of last lecture. That is, how do we do machine learning? In particular, what does it mean to do regression and classification? So just to fix what we have said last time. So if you remember, we start with some finite set of data, this data set, which is an amount of items with the variable x and the label y. These are the examples. These are the training examples. This is the data of a function that we would like to know. Okay, so the problem is we would like to know a function because this is the problem that we would like to solve. We know this function in several points. You remember that we know this function in a noisy way, meaning that also the points are probably not the exact values. So everything is in the realm of approximation. We would like to know this function in the approximate way. And if we have a classification problem, instead of a function, we have a probability distribution. Okay. And we would like to find the best possible approximation of the one or the other. Now, we said the last time that we choose a parametric model. There are also other non-parametric models, but we restrict our attention to parametric models. And so this function is now a family of functions parameterized by a parameter theta. This parameter lives in a high dimensional space. This theta is usually in a vector space of dimension d. And just to let you know, this number, this is the number of parameters, can be in the largest model existing as of today, can be also hundreds of billions. So can be of billions. I mean, something like this. Just to have an idea, this is the maximum number, the maximum number of parameters you can find in a model today. Just to let you understand how fast we are growing with this number. In 2016, when in some sense everything started with AlphaGo, the neural network winning in the game of Go, I think I remember it used to have 60 millions of parameters. So a very smaller number with respect to this number I'm telling you now. Okay. Then you remember that now we are going to find a candidate for the approximation we are looking for. So we are going to find a candidate, and in order to assess how much this candidate is likely going to be a good approximation of this unknown function, we need a test set. And for this reason, we always split in the very beginning all the data we have. That is the only thing that we can use. We split it in a training set and in a test set. The test set is used only to assess the quality of the function that we are now going to find with the training set. Okay. How do we find this candidate function for our approximation problem? Well, we have a loss function. We have some quantity that's telling us how far is the function we are looking for from the function, from the candidate we are considering. And last time, you remember, we used this that could be called L2 distance between the unknown function and the candidate function. This loss in some way indicates how much our candidate is far from the unknown function on the training set. And so in order to find the best candidate with the amount of data we have, we just have to solve a minimization problem. Okay, we have to optimize this function. Okay. So after we find this candidate function, we can test the model. We can test the model by computing the loss on the test set. And if the loss on the test set is comparable to the loss on the training set, we say, okay, I think I made the best I can do with my data. And as Tommaso was pointing out last time, there are no guarantees for certain that we are finding the good approximation, a good approximation of the unknown function we are looking for. But if you remember, as I pointed out, we can have guarantees in terms of probabilistic approximate way. More on this in a few minutes. Okay. Here there are some references. Again, this is in the shared folder. This is a book, very elementary, on artificial intelligence in finance. I think for people that are just starting learning this kind of things, this is a good introduction. I mean, it is very simple, but very, very clear. So this is something I suggest you read, but we are not going to look at this right now. And again, a very elementary introduction to training, validating, and testing, again, in this file. And maybe I can show you this page 6 for an example of overfitting generalization. Yes. So we go here, and I can take this. So, page 6. Okay. Here, what I want to show to you is this table here. Okay. You can see that here there are 3 models. We learned the problem, doesn't matter what it is, there were some training data, but we used 3 different models, not a neural network. These are just polynomials. One model is a polynomial of degree 5. The other model is a polynomial of degree 2, and the other model is a linear model, okay? So it's a very toy problem, very simple problem. And these numbers, you can see here, these numbers are the loss on the training set and on the test set. You can see that for the polynomial of degree 5, the loss on the training set is much smaller than the loss on the test set. And this means that we learned a very good approximation on the training set, but this approximation is not working very well on the test set. And so we say that in this case, we are going in overfitting. And then you can see that both the quadratic model and the linear model, they perform similarly on the training and on the test set. You see that
Maurizio,
Yes?
can we interrupt? There's a question. Just a moment.
I'm sorry, it's a technical question. Some guys can't attend the lesson here, so they ask if the link of this team can be set to public, so they can access, they can see the lesson.
They already can. Tommaso, can you give them the link? Or...
Well, I need some information. Who should I send it to? Just a moment, Maurizio. That's
yes.
If you just send me one, maybe that's enough. And ma cos'è, un numero di telefono o qualcosa?
So the link is this one. I don't know if you want just to copy it.
Si vede? Allora, io faccio...
Tu basta che copi questo e lo mandi a chi serve.
Ok, quindi posso copiarlo da là?
Si può copiare di
una foto. Avvicini e fare la foto. Ecco, così poi...
Ah, ok.
In the meantime, Maurizio, sorry, are you saying that
Thank you.
the space of fifth-degree polynomials is worse than the space of linear polynomials for this problem?
For this problem, yes, because it was a really toy problem, and with the polynomial of degree 5, you were able to completely pass through every point. This is what we were saying last time. Remember something?
But it's the same training set.
If
no?
you have, wait. If you have this point in the training set, and you use a polynomial of degree 5, you will find something that is passing through every point here. Okay, but it's probably not what you are looking for.
Okay, are you using the same training set in all of these parameter function spaces,
Yes.
whatever?
Yes.
No, you're not.
Yeah.
No, quello è loss, d'accordo. The numbers you're giving us are the loss. So
Yes.
Same training set, same validation set in 3 different cases.
In 3 different cases, exactly.
Okay.
And you notice that, so the degree 5 polynomial is not working. This is just overfitting and passing very well through every point. But both the quadratic model and the linear model, they works, and then you can choose the better one. Which is the better one? The one with the smaller loss. As long as they don't overfit, meaning that the training and the test losses are comparable, you choose, of course, the one with the smaller loss. Okay? Okay, if somebody is connecting, I should probably... Okay, here. People admit all. Okay. If somebody else wants to connect, you should tell me, because I have to admit them. Okay. Okay, so this is just an example with numbers to let you get in touch with what we are saying. Okay. Now, this point to here, and this is something a little bit technical, but I wanted to show you what I was talking about, yes, the last lecture about probably approximately correct statements. So I have found slides of a nice course on statistical learning, and in lecture 3 that I have put in the share folder, there is something that I would like to show you. So here, okay. Okay, so these are the slides of a course on statistical learning. Okay, and I want to show you just a few things from here. So, here, the problem as the same problem as no, wait, what I want to say. Okay, imagine I want to do this analogy. This is a bin with a lot of balls, green and red. Okay, and the quantity you would like to know is the number of red or the number of green balls. That is the probability of picking, let's say, a red marble. Okay, so this P is the number that you would like to know, but you do not know. How could you try to know this number? Well, you can take a sample. Okay, you can take random balls from the bin and check whether how many red marbles you picked up. And we know that as long as this sample is big enough, the number we are going to obtain here, the probability of picking a red marble, will eventually converge to the true probability. Okay. Now, what Tommaso asked last time is something that I think is subsumed in this slide. If I have here 2/5 red marble, can I say that for sure in the bin there are 2/5 red marbles of the total? No, of course, I can't say for sure this, okay? And for instance, I could have all the marbles, they could be green also if I picked up 2 red here, okay? But actually, I can say something in the sense of approximation and in the sense of probability. This is what I was trying to tell last time. And in particular, when I take a big sample, when I take a large number of marbles, I can say that our estimate, P hat of the unknown and true probability P, I can say that this number is probably close to P. And this is state, but that inequality I was trying to remember last time without success. This is an inequality that there are several different forms of this kind of inequality. I remember having studied the Chebyshev inequality when I was a student, and here there is also another similar inequality called Markov inequality. They belong to a similar family. And in particular, in this case, we can say that the probability of our estimate, the number of red marbles that we picked up in the sample, to be far in L1 norm from the probability P, the probability that this number is greater than epsilon for every epsilon is upper bounded by this number. And you can see that if the number of items in the sample grows, when this is going to plus infinity, let's say, this number is going to 0. And so this number is in probability close to P. So can we say that P star is for sure P? Can we say this is correct statement? No. Can we say that P star is for sure approximately P? No, not for sure. Can we say that P star is probably approximately P? Yes. So these kind of statements are what are known as PAC statements, probably approximately correct statements. This is what I was trying to tell you last time. Okay, and here there are other nice things on generalization, the in-sample, out-sample error, but let's go on. So, and number 2 is done. Now, let's get back to neural network. Okay, remember, neural networks are computational graph, are parametric functions given by that picture that I explained on Friday, that are computational graph. Okay, they are given hierarchically in some sense with linear components, matrix multiplication, affine multiplication. If you remember, there are bias and weights, and nonlinear components given by the activation function. Okay, now why neural network? What I want to tell you now is why neural networks are so successful in approximating functions. This is because neural networks are universal approximator. That is, for neural networks, you can prove a family of theorems, similar but in different statements, that are called universal approximation theorems. And I will show you the first one, the original one, which is a paper by Sebenko in 89. And I will show you the statement just to let you understand what we are talking about. So theorem 1 at page 4. So this one. Here we are. Okay. So look at this theorem 1. Let sigma be any continuous discriminatory function. What is a continuous discriminatory function is written above, but in our language of neural networks, this is the activation function. And here you see that the activation function can be very general, okay? Then, finite sums of the form, reading this theorem, okay? Finite sums of the form this way, gx equal to the sum. Look here, inside the sum, we have the activation function sigma. As the argument of the activation function, I have a linear transformation plus a bias, so an affine transformation. And then these values are again linearly combined. Okay, can you recognize from here a neural network with 2 layers? Maybe I can try to. let me. So remember, a neural network was something like this. I have x1, x2, x3. Then I have the multiplication by a certain matrix. And let's say here I have, I don't know, 2 nodes, h1, h2, and then another multiplication by another matrix. Here I can have the output. And the neural network, in this case, is a function from R3 to R. The neural network, this function, how it is done? Well, I take x multiplied by this matrix. I sum a bias, which is implicitly given here in this column of neurons, and then I apply a activation function. If you remember, in the computational graph, we used to have function inside the nodes, and then I told you that the function in the nodes is always the same in a neural network, at least on the same layer. In this case, we denote it by sigma. And then again, we multiply by this matrix. Okay, and we add another bias. Let's say for simplicity, we don't have this bias. So we have linear transformation here, non-linear activation function, linear transformation here. Okay, this is the function given by a neural network which has one layer and another layer. So 2 layers neural network. In the theorem, you can recognize exactly the same structure. Okay, activation function, linear function, and linearity outside. So what this theorem is saying that the function computed by a neural network with 2 layers are dense in the continuous function on the hypercube. Okay, this IN is hypercube. So can you understand what this theorem is stating? It's saying that if you have to approximate any continuous function of the hypercube, then you can find a neural network with just 2 layers and a sufficiently big enough number of units, because this n, this capital N here, is the number of units you have inside. So in this case, it will be n equal to 2. Okay. Well, you can find a big enough n such that for any given epsilon, you can find an epsilon good approximation of any continuous function on the hypercube by your neural network. Okay, this is the prototype of a family of theorems known as universal approximation theorems. And as soon as you build a neural network, the first question you ask yourself is this neural network a universal approximator? And in general, the answer is yes. Neural networks are universal approximators. Okay, let me find. Here. Yes, okay. Now, in this other reference here, this is a beautiful online book. And I strongly advise you, suggest you look in chapter 4, because there is a beautiful visual proof of why neural networks are universal approximators. And I can just summarize this proof.
Maurizio, can I ask a question?
Yes.
In your previous example, in which you had a discriminatory continuous function, can that function just be the identity? I mean, if I go from R to R, I don't know, from the interval 0, 1, and I use the identity there, my function G is always going to be a linear function. And
Exactly.
I cannot use it to
The activation function can be any function except polynomials. So the identity is not working.
okay.
So can't be a polynomial. But as soon as you have a non-polynomial function, then the neural network is going to be a universal approximator. Okay.
Thank you.
And I wanted to just give you a very, very quick proof of this fact for neural networks where the activation function is the sigmoid. The sigmoid is a function which is bounded by 0 and 1. So let's say this is 1. The sigmoid is going from here, 0, then here, and then here. Is symmetric. Okay, is sigma of x equal to 1 over 1 plus e to the power of minus x. Okay, this is the most classical activation function that is used. Now, if you compose this function with a affine transformation of x, you will notice that you can modulate this function in this way, in such a way that it is almost horizontal here, and then it goes very steep here, and then do something like this, of course, in a smooth fashion, without this point. Now, as you can see, this means that by linear transformation of the argument, the sigmoid can approximate a step function. And then I would say we are done. We are mathematicians. We know that with step functions, we can approximate continuous functions. Okay, so the reason why in this case with sigmoid activation function, the neural networks are universal approximator is very easy. Of course, when you have different activation function or different structure in the neural network, the proof is a little bit different. And this is just an argument. Okay, and then I want to show you the Wikipedia page on universal approximation theorems. That is also very nice. So, universal approximation theorems are results that put limits on what neural networks can theoretically learn. Okay, in particular, they establish the density of a class of function generated by an algorithm. Okay, neural network is an algorithm if you think this way. And when you have a universal approximation theorem, you can have a theorem that is stating something about there exists a neural network with a lot of neurons in the layer. There exists a neural network with 3 layers, such that in the internal hidden layer, the neurons are a certain number. Or you can have theorems that quantify, in some sense, the depth of the neural network. Maybe they state that there exists, for any function of a certain kind, there exists a neural network with 100 neurons per layer and a certain number of layers. Okay? But what I want to tell you, what I was going to tell you. Okay, the universal approximation property is equivalent to a non-polynomial activation function. This is what I was telling to Tommaso before. So the activation function can be really everything, okay, except for polynomials. And I want you to notice that in 2022, there is a result on precise, there is a quantitative result on the depth and the width of the neural network required to approximate a certain target function with ReLU neural network. ReLU is another activation function, different from the sigmoid. Why I'm telling you this? Just to let you notice that this is a result from the last year, and this is showing to you that despite the fact that the first original theorem was in '89, this is still a very important deductive research field. Because remember, I'm trying to give you some hint on what a mathematician could do as research in this field. The universal approximation theorem is a very active and very important theoretical research field in this in this area. And okay, question here there is the theorem in the form that is usually used, but I wanted to show you that there are also, yes, you can see here a theorem where the class of functions that are approximated is not the class of continuous function on the hypercube bar, but are LP integral functions. Okay, so you can see that these theorems are of the same family, but can be quite different in nature between each other. Okay. If you have questions, please ask. Okay, and I think it's time to talk about convolutional neural network, which is important for the next lecture. Okay, so here there are some points about what fitting and overfitting, what is a problem known as the vanishing gradient problem, and so on. But I don't want to risk having no time telling you what are convolutional neural networks, so we'll skip to this now. Okay, and for this, I will use as material a course I made, I think in this very same school in 2018 in Pisa. The course was Introduction to Neural Network for Mathematicians, and this is something I suggest you to look. There are a lot of slides for this. This is the link, but in the share, I keep the file, and so let's go to this file. Neural network crash course. This one. And then we should go pages 87. Okay. There should be a faster way to a page. Vanishing gradient. Okay, here we are. So, okay, now I want to describe to you a model, a neural network, which is the kind of model, the neural networks which are used as of today for images. This kind of neural network called convolutional neural networks, because you will recognize the convolution operation, the mathematical convolution operation in its discrete form. And they are used for image recognition. The funny part is that the idea for this kind of model comes from how the human eye works. Okay, okay, I'm trying to explain here. So the first observation is that when we have an image, this image is not only a vector. It's not just a vector b in r to the power of 784. 784 is 28 times 28. So this is the dimension of images which are 28 by 28 pixels, okay? But of course, an image is not just this vector. An image has some spatial relations which are expressed by the fact that the values, sorry, by the fact that the values of the image are put in a rectangular shape. You understand what I'm saying? If I give to you an image in this way that is flattened, that means I show to you these lines of points, but not one over the other, but just in a line as a big flat vector, you are not recognizing the image anymore, of course. So we want a model which is able to capture these spatial relations. And for this reason, we copy something that the human eye, the human vision, does. That is what is called the local receptive field. Now, remember how is the neural network? I always describe to you the neural network in this way: neurons, and then two other neurons, let's say just one. And then this value goes here, goes here, goes here, goes here. Every number is multiplied by real numbers, and then there is a fine transformation done by the bias. Okay. Now, since we have now the spatial relation, so you see this picture is the same as before. This is the output neuron, but simply these neurons, the input neurons, are still in their rectangular shape. So let's say we decide to use a local receptive field, as in this case, which is dimension 5 by 5. Okay. This means that I will use 5 by 5 weights. This means that let's say 2 by 2. It's faster. So let's say I use a 2 by 2 receptive field. This means that I will have just 4 weights in this case. Let's say A, B, C, and D. And these 4 weights will be the weights used for these 4 values. I'm not sure I'm explaining. I will try again here. When I have 4 inputs here, I will have also 4 weights here. Okay. And And the value here will be W1 x1 plus W2 x2 plus W3 x3 plus W4 x4 plus B. Okay, this is explicitly the neural network as I was telling you before. And then there will be the nonlinear activation function, but for the moment we are not interested in this. Now, if I have other neurons here, I will have other weights. I will have W6, I will have W5, okay, and other weights here. What I'm saying is that in convolutional neural networks, when I have an image, let's do the image here. In a convolutional neural network, I choose the dimension of the receptive field, let's say 2 by 2, and this means that I'm deciding to use just 4 weights. That means this number will be multiplied by W1, this by W2, this by W3, this by W4, and these 4 neurons will produce in the next layer 1 neuron. Then I will slide this receptive field 1 pixel on the right. And now I have these 4 points. And I will use the same weights for this W1, for this W2, for this W3, for this W4. And these 4 values will produce another point, another pixel, and so on. So I will take this 4, and I will have another pixel. I will take this 4, and I will have another pixel here. I will take this 4, and I will have another pixel. I will take this 4, another pixel, 4, another pixel, and this 4, another pixel. And then I slide the receptive field also on the other direction, on the other dimension. And at the end, I will have 1, 2, 3, 4, 5, 6 pixels in this way. I'm pretty sure I was quite confused. So ask questions so I can try to let you understand. So I'm describing to you a new kind of layer for a neural network where the points are not all connected with each other. I mean, normally in a neural network, if you have these nodes and these nodes, all are connected, fully connected, are connected everything with everything in a layer. In a convolutional neural network, you have connection with weight sharing, meaning that this point here is not connected to every point in the image, but just with 4 points. 4 because I'm choosing as receptive field a 2 by 2 square. Let me get back to this image. In this image, we have a receptive field which is 5 by 5, and this means that I will have 25 weights. It was describing the receptive field is moved around according to its stride. The stride is the number we move the receptive field. In my example before, it was 1, and usually it is 1. So you take this square 5 by 5 and you produce a new value here. Then you move the square 5 by 5 1 pixel on the right, and then you produce this new value here, and so on. Okay, and this is this image here. So this is in a non-pictorial way what I was trying to say. So, like, the important things is that these values, the receptive field parameters, doesn't change when sliding around. Okay, this means really a lot less parameters. I'm not sure you are getting the points. Normally, in a neural network, the kind of neural network I described to you since Friday, in this kind of neural network here, you would have in this connection a matrix of weights, which would be this number of pixels times this number of pixels. Okay, this number of pixels are how many? 4, 6, 10. So let's say these are 32. Okay, I think this is an image 32 by 32. So in a normal neural net, in a fully connected neural network, I mean non-convolutional, you would have more than 900 weights here times the weights here. I mean the matrix would be a matrix of dimension more than 900 times, and this is probably 25, let's say 600. Okay, in the corresponding convolutional neural network that I'm describing here, you have just 5 by 5 weights plus a bias. Okay, so convolutional neural network, thanks to this idea, they allow us to use much less weights. That means that one can do a lot more layers, for instance. Okay. Okay, if one want to write the formula of the output of the neuron is this way. What do I mean? The formula of the output of the neuron. Let's say here I have this image, and I want to know, here I have another layer, which will be another rectangle or square. And I want to know what is the value here for E equal to 1, J equal to 3. Okay. And so this is the formula. You can see in this formula the weights, the linear parameters are 5 by 5. And they do not change with E and J, with J and K, sorry. J and K. Okay. Is there any question on this?
I don't see any questions.
So sorry,
Okay.
There's a question.
trying to learn
Yes.
a bit better about this. The first hidden layer has this structure, has multiple, I don't know. I didn't get how this neural network goes in the next layers. I didn't get the whole structure. So if this is the first step, then after what happens? The next
Okay, you're right. Good question. So let me check here. So in the usual picture of the neural network, we used to have this layer, and then another layer, and then another layer, and then another layer. I'm putting different amounts of neurons, okay? And when I wrote this kind of picture, the meaning was that these three neurons were connected to these three neurons by a linear transformation plus a fine movement, and then nonlinear activation function. And then the same here and the same here. Okay, this is clear, right?
Yes.
Perfect. Now, the only thing that is changing is that instead of writing the neurons, these small balls, these nodes in the computational graph, in a vertical fashion, in a vertical shape, I'm writing them as an image. So, by writing them as an image in this rectangular shape, I can do what I was saying, that is this weight sharing, and I'm now describing to you how I produce the first hidden layer. Up to now is clear?
Yeah.
Okay,
Yeah.
and now your question is how I go forward, right? The next layer.
Yeah.
Okay, this is still a rectangular shape, so you can do the same. You choose a receptive field, let's say 3 by 3, and then you take 3 by 3 points, so 9 weights, multiply them, apply the activation function, and for each block of 3 by 3 points, you obtain in the next layer another node. Okay?
Yeah.
And you see that in this way, at every layer, we will have a rectangular structure. Okay?
And do you because it seems to me a little bit too local as an analysis of the image. So does this structure get a relationship between very far points, or do you I don't know, do you do something in a parallel? I don't know, a global analysis of the image on the whole?
Very good question. So you are saying that this kind of analysis of the image is very local. You are perfectly right. If I'm restricting myself to one layer, then I will be able to get the structure of the image only in a 5 by 5 local neighborhood. Okay, this is, I guess, what you're saying. And so your question is, if there is a relation between a point here and a point here, I will not get it. As far as I use just one layer, I will not get it. But think about it. The first layer is looking at relations here in this shape of 5 by 5 and is condensing this information in this point. And the second 5 by 5 is condensing the information in this point. The third 5 by 5 in this point. This means that when I will use a 5 by 5 receptive field here, I'm taking the information, I'm condensing, I'm analyzing the information coming by 5 points, but each one of these points corresponds to a 5 square here. So you see, by this hierarchy, at the next level, I will analyze not anymore local relation. The locality is increasing. And as soon as you have a sufficient number of layers, then you can get the non-local relations. Is this answering your question?
Yeah, of course, and I got it before, but yeah, it seems to me still a little bit, of course, more local than a layer that gets the data from everywhere. But yeah, of course, it's gathering progressionally, gradually, more and more information and wider. But okay, it's very interesting. But,
so the point is that in this way, you are getting information in a hierarchical way. So there were some picture. Let's say
yeah, what about what about the previous?
Yes.
Video? You have multiple first hidden layers.
Say again, please.
You have multiple first hidden layers. You have more than one.
You mean here in this picture?
Yeah.
Okay, so this is the next point of the convolutional neural network. So what I described to you up to this moment was just this map, one of these three arrows. Okay, let's say this map. So I described to you how to map a 28 by 28 image using a 3 by 3 receptive field to a 24 by 24 image. Now, remember that these weights, these 3 by 3 weights, are shared, are always the same for the whole image. And this means that the point that I'm getting here in this strata, in this layer of the new image, are all describing the same feature. Meaning, if these points, if these weights were recognizing, I don't know, a shape like this, they will recognize a shape like this here, but they will always recognize a shape like this. This means that in this new image, there will be high values where such a shape was present in the previous image, and low values where such a shape was not present in the previous image. But this means that the whole of this image is devoted to recognize, to store information about this kind of shape. Okay? And so what does it mean? If I want to recognize an image, if I want to elaborate an image, to extract good enough information from an image, I cannot restrict myself to recognize a single shape. I will have to recognize several different shapes. So I do the same as I did before, but with another block of 3 by 3 weights. Okay, and I will put the new image resulting just below in this image. In this, I will tile this image one over the other, and this layer, it is called channel actually, not layer. this channel of the first hidden layer will probably recognize a different shape, not anymore this, but maybe symmetric shape, something like this. Okay, so you do this trick on several channels. And so after the first layer, you have a new image, which is made by several channels of points, of pixels. If this sounds strange, because you're thinking, but an image is just a single layer of pixels, this is not true usually. For instance, color images, you know that they are three different combination of colors. Okay, so for an image which is a color image, you have three channels. You have green, the red, and the blue channel. So already an image has three channels. So we are just doing this in the next layers. Okay.
Okay.
Okay. And these are the features learned in a real example with 20 feature maps. 20 feature maps means the channels. This means that here you can recognize a receptive field which is 5 by 5. Okay. And learned weight. And if you represent them graphically with bigger intensity for bigger numbers, darker intensity, darker color for bigger numbers, and lighter color for smaller numbers, at the end, you can visualize the weights learned. Image classification problem, and in this case you have this.
Excuse me.
Okay, this is yes.
So basically, adding one channel is equal to adding like the number of neurons equal to the dimension of the processed image. So in this case, it's 24 by 24. So
Exactly. Adding a new channel in this example, strata of 24 by 24 neurons. Consider that this number is automatically given by the receptive field and the stride. If you start with 28 by 28 and you choose a receptive field 3 by 3, if you count, you obtain 24 by 24, if I'm not wrong. Let me check, because you start here from 3, then 4, 5, and as soon as you arrive to 28, yes, I think you have 24, right?
26.
Of course, it depends also on the stride. If you move by 1 pixel when you move, then you obtain this number. If you move by 3 pixels, then you obtain a much smaller number.
Ritorna a 26 piuttosto?
Mi sa di sì. Yes, that 24 was probably given by a size 5 by 5 receptive field.
Bene. Good.
Okay. So, what I just described to you is what is called, what's the time actually? Okay, we are still a few minutes. Okay, I described to you a convolutional layer. Okay, now a convolutional neural network usually has more components than just convolutional layers. Okay, and so I'm now going to describe another important component of a convolutional neural network. So first, there was the convolutional layer, doing that kind of synthesis of the information in the image. After the convolutional layer, one of it often uses a pooling layer. A pooling layer is in some sort subsuming the local information in just one point, not with a linear combination as before in the convolutional layer, but just by an average or a max or something like this. For instance, in this case, we have a max pooling procedure, a max pooling layer that is just taking these 4 values and putting here the maximum. So in some sense, is making the information more local, because if the maximum is here or here or here or here, it doesn't matter. This layer is saying, I don't care where is the maximum, as long as this number is in one of these 4. Okay, so this is another way of reducing the information, summarizing the information in the image. In this case, for instance, the maximum is 6, and so here we have 6. The maximum is 8, and so here we have 8, and 3 and 4. And notice also that with respect to the convolution is sliding over the image, but this is jumping. These are not overlapping, these 4 pieces. Okay, this is a way to reduce the information. Of course, it's a lossy way of reducing the information. So, in this way, a convolutional neural network would be composed by the convolution first, in this case, 3 channels, 5 by 5 receptive fields, and then the max pooling, which is dividing by 2 the number of neurons. And then we can go on. Okay, from here we can do again convolution and then again max pooling. At the end, when after several layers, not only these 2 layers, but several conv plus pooling layer, at the end I will have in the last layer, I will have summarized the information of the image. Okay, every channel will have taken the shape, whether there is this shape, whether there is another shape, and so on. And then all this information will be subsumed by the pooling. And then again, all this information will be convolved by new convolutions. And in this way, the local information from the original image at the end, in the last layer, will be made global. And so at the end, I can finally collect all the information. Now I have all the information I need, and I can use again a fully connected layer. Okay, so I'm flattening now the final image where there are all the information needed, and then I will output the value that I need. Usually for an image, you have a classification for the image, so the output will be the number of classes for the image. Okay, and this is what is called the convolutional layer, a convolutional neural network. Okay, these are exercises. Just to show you how well this kind of structure works, this is the final output of a problem recognizing images, which has been handwritten, and the neural network is devoted to recognize whether this is a 0, a 1, a 2, and so on. Now, at the end of training of this network, in this example, these digits that I'm showing to you are the digits that were not recognized by the neural network. The digits where the neural network was mistaken. And just to let you understand this kind of problems, this digit was a 6, but the neural network said it was a 0. Would you agree? I guess you agree that this is understandable as a mistake. I mean, this is almost a 0. Here, the number was a 5. The neural network said it was a 3. Here, I think the neural network is right, not a human. The number was an 8, but the neural network said a 9, and I think this is a 9. Okay, this was a 7, and the neural network said 1. Okay, just to understand that such a neural network can make mistakes that are, I mean, also human would make a similar mistake, I think. Okay. There is another thing that I wanted you to understand. That is, okay, this is important for the next lecture.
Sorry, Maurizio.
Yes.
Just to be sure, what you just showed us was the result of a learning process?
Yes.
Is that correct? So there
Yeah.
was some type of convolutional neural network which was trained on a certain amount of data, and
Yes,
after it was trained, they did this final test, and these are you're showing us the results of that training, correct?
Okay, I'm showing you the mistakes after all
Yes.
other. These are 60,000 digits, and all the 60,000 digits have been correctly recognized, except this 33.
And another question in terminology: to learn means to do gradient flow. When you say that a machine is learning, it is computing a gradient flow, correct?
To learn means a step where you modify the parameters in a way that the new choice of parameters gives to you a function which is closer to the unknown function.
Yes. Okay. So it's
usually you do this with a step of gradient descent.
Yes. Okay.
Okay. So important thing is that the convolutional layer is equivariant with respect to translations. And why is that? Because the weight sharing. Because if this convolutional layer is, let me clear a little bit. If this convolutional layer is recognizing in this point, is putting a high value, if there is here a shape like this, since these weights are the same weights that are used here, this means that also here there will be a high value if in this place there is such a shape. And this means that this layer is equivariant with respect to translations. Can you see this? Because if I translate this shape from here to here, then the same value, corresponding value, will be translated from here to here. Okay, so we have equivariance. This will be relevant in the next lecture of tomorrow. Okay, I just want to show you something now. Okay, so I want to show you some examples. Okay, and then we are done. So yes, 5 minutes to 3. So I'm showing to you this 0.8 that are I think impressive applications of neural networks. So let me first open. Okay, so I don't know if you know this website. This website is called "This Person Does Not Exist," and if you just refresh with F5, the neural network behind this website will generate on the fly an image of a real-looking person, but this person does not exist. And you can see the details. Okay, I repeat, this kind of images are generated. Okay, they are not taken by a data set of pictures of real persons. Behind this, there is a neural network that has been trained to reproduce images that are looking as faces of real persons. I could go on forever. Okay. So I think this is quite impressive. Sometimes you can find some artifact. You see here, there is a small detail, which is they are called artifacts in this kind of images. And of course, the other application that I guess everybody of you knows is ChatGPT. This is for those who know that do not know what it is. This is a chatbot, a very famous chatbot, which is impressive. Is able to chat just like a real human, and it is something that if you chat with him without knowing it is a chatbot, you could easily mistake this for a human. And another application of this kind of models is that they are able to write code. So the same thing. You can ask him to write a neural network, maybe convolutional neural network with n layers and max pooling. Good. I repeat, this is a neural network. Okay, what is doing this is a neural network behind. This is a neural network with 5 billion of parameters. And you see, first, explain to me what is going to do, and then now is writing the code. Impressive, right? And then I wanted to show, okay, these are 3 papers that if we have time, I will show to you in the last lecture. This is an artificial intelligence technique called reinforcement learning that has been used to find explicit counterexamples in conjectures in graph theory. This is very, very interesting. Okay, this is not a neural network. This is a technique using neural networks. Is a technique we haven't talked about that is called reinforcement learning. Is the technique used by DeepMind to write the software that beat the human champion of Go. And it is very effective in this kind of tutorial problem. Again, since I want to show you how artificial intelligence can be used by and with mathematicians, this is a paper where deep learning has been used to assist a mathematician in proving theorems. In this case, the theorem was a theorem in knot theory and another theorem in graph theory. And this is very, very nice paper. And finally, another kind of applications for theoretical mathematics. Here, there is a paper where neural networks, reinforcement learning actually, has been used to find a new way, a new faster way to multiply matrices. So you probably multiply matrices by, we all multiply matrices by the row by columns method, okay? But this method is not very, very fast, and with big matrices is not effective. So there is a research topic that is finding new algorithms, faster algorithms to multiply matrices. And here, artificial intelligence has been used to find one of those algorithms.